I get quarantine, I'm showing up.
It's fine with me, but I didn't say that. Okay. All right, so here we go. What is a logarithm? So repeat after me. A logarithm is the exponent. Say it. One more time. A logarithm is the exponent. In math, the word is the equal sign. Okay? So when you see a logarithm, this LOG thing that you see right here on the screen, and then you see an equal sign, X must be what? The exponent. Always. Logarithm is the exponent. Got it? Okay. So logs are used to solve equations like 2 to the what equals 8. Okay. But you don't need a logarithm to solve that one because you could do that one in your head, right? You didn't really need a lot of help. But what if it was like 5 to the what equals 8? Could you do that one in your head? Anybody? 5 to what power equals 8? Does anybody in this room know that?
What the heck? To what power is 8?
Come on, that's second grade.
It's basic. 5 to the what equals 8? I have no clue. I know it's 1 point something, but I don't know what that 1 point something is. How do I know it's 1 point something? Because 5 to the first is 5, 5 to the second is 25, so it's got to be in between 1 and 2 somewhere. Okay, but to actually find it, to actually evaluate that exponent, I'm going to use a logarithm. Okay, so you know how when we're solving, we're trying to get x alone, this part right here, we want to get x alone. Okay, when you rewrite this in its log form, which is this guy right here, do you see how that x is by itself now? So those two things, these two equations are asking the same exact thing. What is x? And x happens to be that exponent that I need to put on a 2 in order to get 8. This is asking the exact same thing. This is saying 2 to what power gives me 8? Or vocabulary, the base right here is 2. The base raised to what exponent gives me, this is called the argument, or the 8. Okay, so we know it's 3, right? Yeah, we said that a long time ago. Okay, so here are a few examples. So let's just peek at these for a second. So the reason log base 10 of 100 is equal to 2, because remember, log is the exponent. Wow. Let's try that. Just rewind. Let's try that one more time. Ready? So the reason log base 10 of 100 equals 2 is because the log is the exponent. Specifically, it's what exponent do I need on a 10 so that I create a 100? And the answer is 2. Okay, so log base 10 of 100 equals 2 because 10 to the second power is 100. All right, make sure your phones are put away, please. You're not learning anything if you're looking at your phone. Log base 2 of 1/8. Okay, now we're going to get into some exponent rules that we haven't really reviewed a lot, so hopefully you still remember these things. What exponent do I need on a 2 to give me 1/8? How does that 8 get shoved down into the denominator? A negative. That's why the answer is negative. So 2 raised to the -3 power is 1/8. So log base 2 of 1/8 is -3. Any questions about that one? You okay? Okay. Yes.
There actually is a song, like a parody.
Of?
That is, what song is it? It's like Fergalicious or something. It actually helped me last year. I
With
listened to it
logarithms?
right before the test. Yeah, it was incredible.
Okay. You need to find it.
Okay.
And we need to listen to it at the end of class today, or maybe at the beginning of class next time, because if it's going to help us, we should use it, right?
It's
Okay.
incredible.
Yes.
Work of art, really.
And I mean, fergalicious. I mean, how could it not be great? Okay. All right, the next example. Also something we haven't reviewed in a while. This little relationship right here. A 1/2 power is the same as a square root. Do you guys remember that? When you have fraction or rational exponents, that's telling you it's a radical. Okay? So just like 3 to the second power is 9, yes? 3 to the second power is 9. So 9 to the 1/2 power is what? 3. So this is saying 3 multiplies itself twice to give me 9, right? What is this saying?
It's saying 9 undoes itself.
9 multiplies itself 1/2 of a time?
Yeah.
Not really. Really, what this is saying right here is what number multiplied by itself twice gives me 9. Because it's in fraction form, because it's what's in the denominator. Yeah? Do you guys remember converting back and forth between like this? So 9 to the 1/2 power equals the square root of 9. Or let's go crazy for a second. 2 to the like, I don't know. Let's not do 2. I lied. Where's my rat? What if I asked you to do 8 to the 2/3 power? What is that? Cube root of 8 all squared. Yeah, so the denominator is the index on the radical. Say that. The denominator is the index on the radical. Okay, so this 3 right here makes this a cube root. This 2 right here makes this a square root. Okay, the 2's, we just don't write the 2's. Why? Because it's so common. I mean, a square root, come on, you know? Yeah, it's kind of the same idea. Like when I just write an x, everybody knows that's 1x, right? But because everybody knows it, I don't have to write it. Same principle. Allie.
So would you square the entire thing? So it's like you take the cube root first? Or could you put the squared on 8?
What a great question. I have a question for you then. Which one is easier? 8 times 8 first, then figure out what times itself 3 times gives me 64. Or figure out what times itself 3 times gives me 8, and then square that. Which one's easier? Guess what? One of them is definitely easier in this situation, but they are the exact same thing. Okay? Do you remember in order of operations where we have PEMDAS, yes?
Yes.
We have parentheses, exponents, multiplication and division, addition and subtraction. These are both part of the exponent. So it doesn't matter which one you do first. Okay? So squaring it and cube rooting it are technically both exponents. So it doesn't matter which one we do first. That was an amazing question. Okay, what else? Yeah? Okay, so back to our logs conversation. Okay, if we would have had time to do a day of just exponents, that would have been a party, but what? Time? That would be weird. Okay, so we look at this guy. So log base 16 of 4 equals 1/2. Because 16 to the 1/2 power is 4. Yeah? Okay, hold on. I gotta see. Nobody even joined our Zoom class. Should I just? No, it's fine. We'll just keep recording. It's fine. They're all sleeping still. That's okay. All right. Any questions on those examples? No? Okay, a couple of quick properties then. Just stare at those for a moment, would you? Let them sink in for a second.
I don't know, like,
What do you
the
mean?
last one.
You can have an exponent
Not for long though. It doesn't stay there very long. You can pull it right out.
Oh,
Yes, it can exist. If it helps you, think of A as maybe the number 2. Or think of A as maybe the number 5. It won't make a difference. So this is just a very generic rule. If it's not making sense to you in its super generic alphabet form, then you go ahead and think of it another way. Okay, how do you feel about the first one?
I like the first one.
Can someone explain to me why that first property exists?
Because say like 2 is 8, 2 to the 0, anything to the 0th power is 1.
There we go. Because anything, so this doesn't even matter. Because anything to the 0 power is 1. So if you're trying to take any base imaginable and raise it to some mystery power to get 1, 0. So if you ever see a 1 in the, what's this place called? Argument. Very nice. We only said that word one time. Okay. Argument. If the argument is ever 1, what's the exponent? 0. Done. Okay. This could be the most hideous number you've ever seen in your life. Should we make it hideous? There you go. Still just 0. Yeah? Okay, I gotta take it back because that's really ugly. Okay, this one. Someone explain that one to me. Anything to the first power is itself. Yeah, can you guys hear Abby? We're all masked up, so not really, but anything to the first power is itself, right? So if my base, yes, base, and my what? Argument. If they match, then I'm trying to get 3 to what power is 3? 1. 17 to what power is 17? 1. Yeah? Negative 65 million to what power is negative 65 million? Still 1. Okay. All right. So those seem pretty straightforward, yeah? Okay, this guy. What happens here? Oof.
2 exponents to the 6.
Oof. That's a little gross. Yes. Okay. Would you like to say it louder? Oh my gosh. So, Abby just said it's because a to the x is a to the x. Okay, so back to the log question. The log question says a, well, that's to what power, I don't know, equals the argument, which is a to the x. It's got to be x. You see it? Later on, I'm going to teach you a little trick about this guy. Anytime there's an exponent up here, we're going to take it and we're going to drop it. Yes, please. One more time. We're going to drop it. Yeah, we are. Okay. So we're going to drop that x in the front. And then what did we decide log base a of a was?
1.
What's x times 1? So 2 ways to look at that one. Either way, doesn't matter. Whichever way you like better. Okay? All right, now this guy. Woof. Woof. What is the relationship between a logarithm and an exponential function? We haven't really gotten into this yet. We were waiting until we got to graphs, but we got to know it. What is the relationship between a logarithm and an exponential function?
They are buddies.
Say it louder. They are like inverses. They are inverses, yes? What do they do to each other?
Inverse.
Which means what?
Undo each other.
Yes, they undo each other. Just the same way that squaring and square rooting undo each other. The same way that adding and subtracting undo each other. So this is exponential base A. This is logarithm base A. They poof, undo each other. X.
What?
Like, we are going to get to the point where we're solving, and if we have like log base 2 of 5 equals, give me some, we'll just do X, that's fine. Yeah? If I'm trying to solve this, watch what I can do. 2 raised to the log base 2 of 5 equals 2 raised to the X.
Because that equals the same.
You know how when we solve equations, we do the same thing to both sides because we're trying to get X alone? Same thing, same principle. I can take an equation, two things that are equal, and make them both exponents on an exponential, and watch what happens right here. Chow, gone. Just 5. Yeah.
But if the 5 was an exponent, then how do you
Because it's not in an exponent anymore because I destroyed the exponential function and the log that it was inside of. No, it's just 5. I know, it's a little uncomfy. It'll be easier when we practice, I promise you.
So could you cancel out those two on that equation? The A. So it's just X equals X.
And then to get the 2 from the log base 2, like that's what you.
That's why I chose 2. Yes, absolutely. Did you guys all hear that? So because that equation, or because that logarithmic equation was base 2, I use exponential base 2 to cancel it. If I had made both sides exponential base 3, nothing would cancel. I just made the problem way worse. Thank you. Yeah, don't do that. Okay. Now we're going to talk about graphing. Nope, we're not actually. I lied. We're going to do this first. So 2 things. If you ever just see LOG with no base on it, that's a base 10. Do you remember learning that last year?
Yes.
Why do we like base 10? Do you remember from last year why we like base 10 so much? Because it's in your calculator. The other bases aren't in your calculator. You cannot do a log base 2 in your calculator. You cannot do a log base 7 in your calculator. You can't do a log base 65 million in your calculator. You can only do a log base 10. So just like other things that are common or that everybody knows, that log button is a base 10. They just don't put it on there because everybody knows that it's base 10. Yeah? So that's the common logarithm. That's what we call that one. Okay? Logarithms were actually designed to help us understand things that were very exponentially large, like magnitudes of earthquakes, populations that just get completely out of control, like bacteria growth, stuff like that. Okay? We use a base 10 when we're talking, like when you guys learned, wow, what's it called? Scientific notation. Yeah, in math, it's, or in science, it's like 6.73 times 10 to the yada yada, right? Do you know what I'm talking about? 6.022 times 10 to the 23rd. What's that? Is that weird that I still remember that? Is that even the right number?
Wait, what is it?
6.022 times 10 to the 23rd.
Oh, isn't that what?
Isn't that something in chemistry?
That is. It is.
What is it? It's a mole, right?
Oh, yes.
Yeah. Woo! Look at me. Guys, I was a chemistry major for about 75 seconds. And then I was like, oh, the only thing I really like about chemistry is the math. Maybe I should just stick to what I'm good at. fine. It's fine. Okay. All right. So common logarithm is base 10 because we are generally talking about huge numbers using base 10. Okay. The natural logarithm, we talked a little bit about e last time. We have exponential functions that are base e. And we discussed how that's like the natural growth base. Okay. A natural logarithm written with an ln. Yes? So it looks like you would read it log natural. Nope. You read it the natural log of x. Yeah? So everybody look at this. Oh. Why? What did I do? Please stop. Oh yeah, that's probably a good idea. Okay. So ln of x is just the natural log of x. Say it.
ln of x is the natural log of x.
Okay, not log natural, not in. I have people be like, why did you write the word in? I didn't. Promise. Okay. All right, so that's natural log, which could be rewritten this way. Okay, if you would like to see with your eyeballs, if you would like to see the base, then you can write it just like that. Same with this one, with the common log. If you want to see the base, if that helps you to solve the problem, then just rewrite the problem log base e, or rewrite this one as log base 10. Yeah? Okay. Yes.
So can you not do it in a calculator unless it has a base 10?
Oh, you can also do it in calculator if it's base e. So the natural log. So grab a calculator. You're going to need a calculator today. There's calculators on the back counter if you don't have one in your possession. At least I think you need a calculator today. Do you see a log button on your calculator? An LOG. If you see an LOG, then somewhere really nearby, really close, there should be an LN. Yeah? But there aren't any other bases. Now, I always have someone that's like, ha, you lied, because there are. There are calculators, specifically Casio brand calculators, that make life so easy for you. And every time you push the log button, it basically says, what base would you like? I'm at your service. What base would you like me to use? So there are calculators out there that can do base 2, base 3, base 7,000, whatever base you want. Okay. But it's not part of like the normal makeup of a calculator. I guess it's not normal programming. Really what your calculator is doing inside of it when it asks you for, when it allows you to do a base 2 or a base 3, it's going to do a formula inside of it that still uses base 10 or base E. We're going to talk about that later. Okay. Your calculator still isn't actually doing base 2. It's kind of strange. It just converts it for you so that you don't have to do that part of the process. Okay. All right, so did everybody find LOG and LN on the calculator? Yes? Okay, great. Okay, so now we're going to talk for just a second about graphing. Okay? Because logarithms are the inverse of an exponential function, obviously the one with the same base, so we kind of mentioned that earlier, but that's going to be super important. Because they are inverses of each other, then every x and y ordered pair is going to swap places, okay? So if I have the function y equals 2 to the x, it will have, and we talked about this last time, right? There are those 3, we call them like anchor points, those 3 super critical points for the function y equals 2 to the x, okay? They are -1, 1/2, 0, 1, and 1, 2. So everybody remember that from last time. Yes? When you're graphing y equals 2 to the x, these are the main 3 points. Now, adding other points is going to make your graph prettier and more accurate and better, but you have to at least have these 3 points if I ask you to graph that. You need at least that many in order to perform transformations and yada yada. Okay? So I'm going to use those same 3 points to teach you about the graph of log base 2 of x. Anytime two functions are inverses of each other, the x and y's swap places. The input becomes the output becomes the input. So when these swap places, that means that our 3 main points or our 3 anchor points for the log graph are going to be 1/2, -1. 1, 0, and 2, 1. Do you have to memorize those? No. Because every single time you're asked to graph log base 2, you could just say to yourself, self. Do I know the 3 critical points for exponential base 2? Write those down, do a quick swap, there they are. Yeah? Not necessarily something I want you to memorize, something I would prefer that you understand. Yeah? Okay. The other thing is these graphs have an asymptote, right? Y equals 2 to the x has an asymptote. Does everybody agree with that? Where is the asymptote for the graph y equals 2 to the x? It's the x-axis, right? What's the equation of the x-axis? Y equals 0? Yeah? So if everything is swapping, if all the x and y's are swapping, where is our new asymptote? X equals 0. Okay, so I'm going to show you this on a graph because that might help. Oh, there's Landon. Good morning, Landon. Okay, now I'm going to share a different screen. I'm sure he loved that surprise that, you know, everybody got to say hi. Okay, so now we're going to look at this screen for a second. So we just talked about y equals 2 to the x. We've got a point at -1, 0.5, a negative or a point at 0, 1, and a point at 1, 2. Yeah? So if I'm going to swap all of those, I am going to use the point, just kidding, right here. Swap those two. Okay, do you see my new orange point? Yeah, so I went from -1, +1/2 to +1/2, -1. Okay, and then we went from 0, 1 to 1, 0. And then from 1, 2 to 2, 1. Can you see visually how those dots are all a mirror image across the line y equals x? That green line right there? Yeah? So if I go and connect all of those, do you see how this one has an asymptote right here on the x-axis? Now my new graph is going to be approaching but not touching the y-axis. Do you see that? Okay, so this blue graph right here, this is the graph of log base 2, which is just the mirror image of the graph y equals 2 to the x. Okay, any questions about that? Okay, cool. It also works, hold on, I gotta turn all these off. It also works. What's the difference between 2 to the x and this 1/3 to the x that I just graphed? What's the difference between those two types of functions? Okay, we call them exponential growth. And what's the purple one? Decay. So you can also take an exponential decaying function right here and find its logarithm. So the log base 1/3. What's that going to look like? So I'll take like this point, right? And it's going to go here at 1, 0. And I can take my other anchor points and swap them. But it's going to be a mirror image across that green line. So imagine what that might look like. If I flip this purple, this lower purple section over the green line, where's it going to go? It's going to go up here, right? Yeah? Okay, I'll show it to you. So do you see how this purple section becomes this orange section up here? Yeah? And this purple part over here that's above the green line becomes this orange part that's now below the green line. Everybody okay with that? Okay. All right. The only other thing that you need to be able to do is graphing with transformations. Okay. So if I've got y equals 2 to the x right here, and I transform it, what does this do? Can you see this right here? What's going to happen if I just make the x negative? Can you guys tell me? Can you predict what the graph is going to look like? Reflect over what? Reflect over y. There it is. Okay, so you would take those basic anchor points, the 0, 1, nope, just kidding, 1, 0, sorry, 2, 1, and the 1/2, -1 right here. And you would just flip those over the y-axis. Okay, what is this one going to do? If I put a negative in the front of the whole function, that's going to flip over the x-axis. So a mirror image over the x-axis. Okay, what does this one do? To the left one. Do you see it? Yeah, pretty easy. Okay, cool. All right, so the last thing I wanted to mention is the most popularly occurring exponential function ever, e to the x, also has its own inverse function. So we're going to flip it over that same green line. It looks kind of the same, right? Does it make sense to you that y equals 2 to the x and y equals e to the x look almost identical? It's a tiny difference. 2 to the x versus e to the x. E is 2, just 2 point something. I always forget. I can never hold that number in my brain for much longer than 10 seconds. Okay? And then, same idea. This natural log looks a lot like log base 2. Is it 2.718? I need to put it up on my wall like pi, so I'll put it on that way over there, so then I can look at it and you guys won't even know that I didn't know it. I can just, there it is. Okay. All right, so natural log of x looks the same. Transformations work the same. Yes, nothing is scary or different when it's ln. We all agree that nothing is scary or different when the function becomes ln of x. Right? We're just dealing with this crazy weird decimal. Okay. All right. So your assignment right now, well, you have 2 options. So we could keep going. So that's your 4-3 lesson. Okay. If that doesn't feel like too much and too scary, we could keep going and do the 4-4 lesson today and then just do homework next class period. Or we could do the 4-3 homework right now because you still have like 35 minutes and then just do the 4-4 lesson and the 4-4 homework next time. It doesn't really matter to me. The 4-4 lesson is just, do you remember this stuff? Where do I have it? Hold on. Give me a second. Hi. Okay. Oh. Okay, sorry, I made it mad. Where did I put? Okay, do you remember this kind of stuff where if the 2 logs are being added together, but they have the same base, you can smush them together using multiplication? Or if you subtract them, then it becomes division.
What? Wait.
Okay. I think maybe that's not a good idea.
Yeah, next time.
Should we do that next time? Okay. Okay, so we'll be done for today. Okay, so go ahead and work on your 4-3 homework that is posted in Canvas. The notes that I just gave you, are posted. And the graphs, you have access to the graphs on Desmos. There's also a link to that in Canvas if you need it. Yeah, but your 4-3 assignment is already there on Canvas, ready to go, waiting for you. Good? Okay. All right. Landon, we're out of here.
Bye, Landon.
Oh, he's gone. That was quick. He didn't even want to wave goodbye.